In section 4.3, we're going to talk about where electrons really live. We're going to learn how to write electron configurations. So as seen in the previous section, electrons do not live in a hotel. They are in the area outside the nucleus called the electron cloud. The electron cloud is broken down into energy levels, which are sometimes called shells. The energy levels are broken down into sublevels, and the sublevels are broken down into orbitals. The orbital is the region of space where there's a high probability of finding an electron. If we were to take a look at the hotel example, the orbitals would be the actual rooms of the hotel. The sublevels would be the area of the hotel. The principal energy levels would be the floor of the hotel, and the electron cloud would be the hotel itself. The first thing you need to know is that there are only 7 energy levels within the atom. We're going to use the periodic table as a tool to help us with electron configuration. So the first thing that you need to know is that each row on the periodic table, which is called a period, is going to correlate to an energy level. On your periodic table right now, I would like for you to write in the 7 energy levels, or the 7 rows. The lower 2 rows actually go with the 6th and 7th row. So this is still part of the 6th period, and this is part of the 7th period. If you take a look at calcium, you will see that it is in the 4th energy level, and so it will have electrons up to the 4th energy level. Chlorine will have electrons up to the 3rd energy level because it is found in the 3rd row. The first subshell that we need to speak about is the S sublevel. It contains only 1 orbital, and it can hold a maximum of 2 electrons. If we use the periodic table to help us with electron configuration, we will box in the group 1A and 2A elements, and those will correlate to the S subshell. Helium is part of that S subshell, so a lot of times I'll have you guys draw an arrow next to hydrogen to remind you of that. The next sublevel that we need to talk about is the P subshell. It is dumbbell-in shaped. There are 3 orbitals within it. Each orbital holds 2 electrons, to give the p sublevels a maximum of 6 electrons. On your periodic table, you will need to draw a box around all of the group A columns from 3A through 8A minus helium. This is going to give you the P subshells when we use the periodic table as a tool for electron configuration. The next are the D subshells, or sublevels. There are 5 orbitals in the D sublevel. Each orbital can hold 2 electrons, giving a maximum of 10 electrons found in the D sublevel. They are 4-lobed in shape, as seen in the pictures in the upper right. On the periodic table, you are going to draw a box around the entire transition set of elements, which is the group B elements. One of the things I want to point out at this time is that the energy levels that you had written earlier, when we get to the D block, they are slightly modified. When you are in the D block of energy level 4, you are really only going to be in the 3D sublevel, in energy level 5, the 4D sublevel, and so forth. So a lot of times what I'll do is I'll put a little star out here, and we'll put on the periodic table N-1. N stands for energy level, -1. To remind you that you'll be in the 4th energy level using the periodic table here, but as you move into the D block, you will then be really only in the 3rd energy level. The last set of sublevels we need to talk about are the F sublevels. They're too complex to actually give a name to the shape. There are 7 orbitals. Each orbital holds 2 electrons to get a maximum of 14 electrons. And in the periodic table, the first time you'll see them is in the 4th energy level. So electron configuration is basically just recording the address of an electron. There's a couple of rules we need to remember. The first rule is that electrons must be placed in the lowest energy level first. We're going to call that its ground state. When we write an electron configuration, we will always refer to an electron set in each energy level, subshell or sublevel, and how many electrons are within that subshell of that energy level, as seen in the designation for P1. As mentioned in the previous slide, there is a certain filling order. Hopefully this slide looks familiar. It looks very similar to the electron hotel. The filling order is going to be 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, and 6p. Subshells are filled from the lowest energy level to the higher energy levels. This is called the off-bow principle. Electrons must fill the lowest available subshells and energy levels before moving on to the next higher energy sublevel. Once again, the filling order is seen below. You can use the periodic table as a guide to fill from the lowest to the highest sublevels, or you can memorize the filling order seen above. Orbitals can't overlap within different energy levels, and you will see that in areas like right here at 4s and 3d, 5s and 4d, 6s, 4f, 5d, and so forth. If you're going to use the periodic table to help you with electron configuration, you want to remember your blocks S, P, D, and F, and of course your energy levels. So here you can see a periodic table where the symbols have been pulled out and the energy level sublevel designations have been written in. When we read the periodic table to help us with electron configuration, we read it like a book from left to right, from top to bottom. And so once again we can see this filling order: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. Remember that we are moving down into the F block, so then we have 4f. We move back up. 5d, 6p, 7s. We're going back down into the F block. 5f, back up, 6d, and if we had any more elements at this point in time, we would go to 7p. Alright, so let's go ahead and do an electron configuration using the periodic table as a tool. The first thing you need to do is determine the number of electrons that will be found in sulfur. We know that sulfur is number 16 on the periodic table. That means it has 16 protons, and because this is a neutral atom, it's going to have 16 electrons as well. We're going to follow the filling order, and we're going to use the table to help us with that filling order. We always start off at energy level 1, and we visit the S sublevel first. Then we go to energy level 2, visit the S and the P sublevel. We go to energy level 3, we visit the S and the P sublevel, and if we need to go further, we continue. We will be stopping at the 3p sublevel. So when I write my electron configuration, we always write the energy level and the sublevel. So this is 1s, and I have each block is going to represent an electron, so that's 1s2. I'm completely filled in the first energy level, so I'm going to move to the second energy level of the S block, and I'm going to use the 2 blocks to represent the 2 electrons and put a 2 up at the top. I'm then going to move over to the 2p sublevel, where I see 1, 2, 3, 4, 5, 6 blocks to represent 6 electrons. That completely fills the second energy level. I'm going to the third energy level, where I have the 3s block. Electron 1 and 2 will go there. I move over to the 3p block, and I'm going to count over until I get to element number 16, and that gives me 4 electrons. So my electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. At this time, I just want to mention that the highest energy level is the third energy level, and there are 2 and 4 electrons in the third energy level to give me 6 valence electrons. If you remember from the earlier section of 4.1, where we talked about the group number of A block elements representing the valence number of electrons, you will see that those two numbers match. All right, let's take a look at a second example. This time we're going to write the electron configuration for potassium. And you can see that potassium is number 19 on the periodic table. So that means that it has 19 protons in a neutral atom. That also means 19 electrons. So we need to write the address for 19 electrons. As we said before, we're going to start with the first energy level, and we will take out as many electrons as we can per the S sublevel, which is only going to be 2. So we have 1s2. Our first energy level is filled. We're going to go to the second energy level. We're going to visit the S block, and we have 2 electrons that can fill in there. That's 2s2. We're going to move over to the P block, and you can see that there is a maximum of 6 electrons in the P block, so that's 2p6. We're now completely filled in the second energy level. We're going to move to the third energy level, where in the S sublevel we can put 2 electrons, that's 3s2. We move over to the 3p block, and we can put in another 6. And that then leaves us to go down to the fourth energy level. Now there is another orbital, the d orbitals, in the third energy level, but this is where one of those overlap scenarios takes place. We can only get to the 3d orbitals once electrons have been filled in the 4s orbital. So the periodic table, as a guide, takes you through that kind of anomaly. And so in the fourth energy level, you will see that there is the element that we want, and we're only going to put 1 electron in the 4s energy level. As mentioned earlier, the highest energy level is 4. That means that there is only 1 valence electron in potassium, and if we go up to the group A block, you can see that 1 is the group number, so those correlate. Right, the last example that we're going to do is we're going to write the electron configuration for titanium. You can see that that's number 22 on the periodic table. So once again, using our table to help us along, we have to fill 22 electrons. We're going to go to the first energy level, and only 2 electrons can be placed in the first energy level of the S subshell. As we go into the second energy level, there is a 2s and a 2p area. We can see here that only 2 electrons can fit in the 2s sublevel, and we've got the 6 electrons for the 2p sublevel. We now go into the third energy level, where we have the 3s, the 3p. We've got 2 electrons in the 3s, and once again 6 electrons in the 3p. We move to the fourth energy level, and we have a 4s sublevel where 2 electrons can be placed. And now you can see that we are actually entering into the D block for the first time. Remember that the energy level is really 1 less than the row that you're in. So this is the start of the 3D sublevel. And then we count over how many? 1, 2. When we do valence number of electrons, we're looking for the highest energy level, which in this case is the 4s. It's not the last orbital we put down. It is the highest energy level of 4. And so we would say there are 2 valence electrons in titanium. Notice that there is no group A here. This is a group B element, so we cannot use the group numbers to help us with that correlation. There are 2 other rules, and we will see these rules in action in the next unit. Hund's rule, which says that when you have more than 1 orbital, that would be the P, the D, and the F sublevels, that each orbital is of equal energy. We must put an electron in each orbital first before we go back to make a pair. And the Pauli exclusion principle, which says that when 2 electrons are in an orbital, they must have opposite spins. And you can see in the picture below that we use arrows to represent our electrons, and opposite spins would be an up and a down arrow. You can see in this example that there are 4 electrons in the p orbital, and we would put them in as 1, 2, 3, and we go back to make the 4th full in the first orbital.